Hello everyone, welcome to second experiment on digital signal processing lab. My name is A. Sai Madhav. So in this experiment, we are going to apply the different filters on ECG signal, just like we have applied last week on PPG signal. So before going to the experiment, I would like to show some of the results which we have taken after measuring the real-time PPG signal. That means we have taken a PPG sensor and we have measured the PPG signal and we have done the analysis on it. So I would just like to show briefly how the images would look like. So this was the real-time PPG signal and we have filtered it. Like it's almost similar, but we wanted to ensure that even if we are applying on a real-time signal, not just on some data which we have taken, we would get the same results. So this is a filtered one using simple moving average. This is a first order derivative, 3-point central difference, and this is the baseline removal one. Okay, so now getting back to the experiment, what we are doing is again we are applying the moving average filter, first order derivative filter, 3-point central difference filter, and here the value which we have chosen, like the number of samples taken at a time, we have to choose it differently. I'll show you the reason clearly. So moving on, as explained, simple moving average filter is used to smooth out the signal, and what we do is we take out L samples at a time and we average them, and that is taken as that instant. So what does L samples mean? The current value, the previous values, the summation of all of them. Now what is the problem with this simple moving average filter? As I explained clearly, if we take more number of samples at a time, and it might blunt out the sharp edge which a signal might have. See, due to that we might lose the information of the signal. So we have to choose the L value clearly. That means the number of samples if taken properly, so that we don't lose the signal information. And first order and 3-point central difference, as I explained, the equation itself speaks y of n is equal to x of n minus x of n minus k. We are just taking the difference. For first order derivative, it is x of n minus x of n minus 1, so which is basically the slope, and a 3-point central difference, y of n is equal to x of n minus x of n minus 2. Moving on. So these are the codes which I have run for data taken from an ECG signal, and what we did is we again analyzed them, and I'll show you these outputs clearly in the Arduino programming. I've taken two different data for ECG signals and two different simple moving average filters, and the results are nearly similar. Okay, I'll just show you the Arduino programming now. So this is the code I have with me. What I did is, instead of taking 8, I took 8 last time, right? So this time I've taken 3. I mean, like, I'm taking 3 samples at a time. I'll show you the reason now. So what I'll do is, first I'll run this, and as I explained, the reason is that this ECG signal has a very sharp peaks. I'll show you the plot clearly. See, ECG has a very sharp peaks. If I take more samples at a time, I might lose this peak now. So I'll show you now if what happens if I use a filter of length 8. So if I take 8 samples at a time, if I'm averaging them, and if I see the output, as I explained, it will be blunt. So I'll just 1 second. See, as I explained, the peaks are clipped off. So most of the part is retained, but the peaks, they are being clipped off. So if I do an analysis on a signal which I have a clipped off, I don't think I'll get proper results. So we have to choose a filter properly. So this is what it simple moving average filter does on a ECG signal. And now what I'll do is I'll go with first order first order derivative, 3-point central difference, and again baseline removal. So this is my code for the first order derivative filter. As I did a simple moving average to get my smooth signal, and then I applied the first order derivative. So now I'm sending this. So I'm opening the serial plotter now. As you can see, this is my central reference, and you can observe that whenever there is a sudden rise, you can observe the increment here also. And this is what we generally see, the first order derivative or 3-point central difference. What we observe, what we used to observe for the ECG signal. And moving on to the second 3-point central difference. See, now this is my 3-point central difference. See, the whatever the signal order I get here, it depends on what I'm writing in the code. So this is my filtered 3-point central, and this is unfiltered. Okay, so moving on, and I'll just show the baseline removal. See, this is the code for baseline removal. I'm just zooming it for you guys. Okay, so the code I've written here is again pretty simple. For baseline removal, instead of taking 800 samples, I'm taking 300 samples at a time. And now what I'm doing is I'm just subtracting the both moving average filter outputs, and what I have to get is the signal which has a baseline removed. That means whatever external noises, low frequency noises the signal has, it must be removed from the signal. And after removing the baseline signal, see, the signal is pretty much similar, and this is the red line here is what I have is a baseline signal, and this is my output. So I've taken with another set of data also, and the filter I've used is, instead of taking 3 samples, I took 2 samples, and the results are pretty much similar as I've shown in the pictures here. Same ECG output, first order, second order, and baseline removal. So thank you guys for watching this video, and I'll come back next week with another experiment.